Hello everyone, welcome to the fourth lecture of Anatomy of Pytorch XLA. Before we get started, as usual, let's have a quick recap of our last lecture. In our last lecture, we really dug into how Pytorch code gets turned into an XLA executable. We introduced 5 main parts of that process: the atom Pytorch integration, the XLA tensor, XLA node, XLA operation, and XLA computation. We walked through a super simple example to show what each component does and how they are related. I hope you now have a solid idea of how Pytorch XLA works under the hood. In today's lecture, we're going to use a real-world example to show you exactly how to take an existing Pytorch code and adjust it to run on XLA devices using Pytorch XLA. Plus, I will share some handy debugging tips. Let's move into our notebook to take a look at today's example. In our first example, I will show you a plain Pytorch code without using Pytorch XLA. And when we scroll down, we can see the body of the model definition. Here are standard imports. It doesn't contain Pytorch XLA specific packages or modules. And this training RESTnet base is our main training class. At the first part, we initialize some constants. And then we specify the device that we want to use is CPU. The next step, we will prepare our training data. Because this is just a demo, I use a synthetic data set. We just generate the images and their labels as zeros and put the dataset into the data loader. We define our model, optimizer, and loss function. Now we have the main part for our Pytorch training. This is a helper function that we can print our training progress. This is another helper function to call the optimizer step method. The step function is one step of our training loop. As you can see, it first set the zero gradients to the optimizer, then run the forward pass of the model, calculate the loss, and run the backward pass. Finally, we change the weights with the optimizer. The training loop is right here. First, we set the model mode to training. Then we create a data loader iterator using a data loader and the maximum steps that we set previously. In this case, the number is 100 steps. Next, we start the timer to record our start time. Then we have our main training loop. It will load the data and the target and use the step function that we defined previously to train the model. Here, we print the progress every 10 steps. Finally, is our main training function. For each the epoch, we will run the training loop. In this case, we only train one epoch, and it's good enough for the demonstration. In the next block, we instantiate the training class, and then start the training. It's a very simple Pytorch example with clearer components and steps. Also, it has a relatively realistic model complexity. Now, let's start our training. We run the first block, then we run the second block, which contains our training class. This is the first time that I run the script, so it takes a little bit of time. Now it's complete. Let's start our training process. As you can see, it starts the first 10 iterations, then the second batch. Here, it prints out the average speed for the last 10 steps. We can see here, it processes about 65 samples per second. Now, the training has complete within a minute. We can see here, it prints 10 times. And this is the training speed. We have about 65 samples per second. And we can see the loss decrease. Now let's modify our code to make it use XLA and train on TPU device. The very first step is to import our Pytorch XLA package. And then let's move down. The same parameters, but different device. Here, instead of using the CPU, we want to use torch XLA.device to let it automatically load the XLA device. So here is no longer CPU, but will be TPU. We have same data set, same data loader, same model, same optimizer, same loss function, same printing function, and the same training step function. Inside each of the training iteration, we need to build our computation graph and let it run on the XLA device. Remember that all the training logics are encapsulated in the step function. So just right after the step function, let's explicitly trigger our XLA compilation and execution. So here we have a torch XLA.sync. So here we call the syncing function. Let's also add a tracker here to track our progress. We have tracker equals XM rate tracker. Then let's import the module here. Because we use the tracker here, let's use the tracker to track our progress. Before here, instead of using total examples, we use tracker equals tracker.add self batch size. Okay. Let's also modify the logging logic. Instead of using this, we use the tracker here. And of course, we need to update our update function right here. Instead of taking a number, now we take a tracker. Then we have this, use tracker.rate. Good. Remember from the last lecture, in order to trigger the compilation and execution of the computation graph, we need to ensure that the data is on the XLA device and the model is on the XLA device. Finally, we need to ensure the trigger of the compilation is there. We just modify our code to have an explicit trigger here. And in the model definition, we already put our model to the XLA device. But how about the data? The default Pytorch data loader will put the data on your RAM, which is for CPU. So we still need to put the data on XLA device. So here we have put training data on XLA device. The function we use is from XLA parallel loader. Here we import the module and we pl.mp device loader. We put our regular training data loader here and we set the device. We assign it to a variable. And in the training loop, instead of using the regular train loader, we use our train loader with XLA device. So now we ensure that we have a data and the model are on the XLA device, and we have a trigger that triggers the compilation and execution of the computation graph. Let's run our function. Here it runs, and it says no module named Torch XLA. That is because we're in Kaggle. We need to have a runtime that has TPU device. It's simple in Kaggle. We just open the side panel and change our session option to have accelerator TPU V5. And it will tell you it's not unlimited. You have 20 hours per week, and we turn it on. It will stop the current session and start a new one for me. Now we have our TPU session open. As you can see here, we have a TPU usage. Let's start running our code. First cell, second cell, and start the training. This is the first time I run it, so it will take a little bit time. Here are some warnings. It's okay. Just still loading those modules. Here we encounter the error. Let's see what's going on. Oh, that is because here we need to remove the train loader from the class scope. Let's do it again and start our training. Now the training starts. As we can see, it goes really fast. The first few iterations are slow, but once it's warm up, we get on average about 760 samples per second. Remember how many samples we have when we train on CPU? It's about 35. So here we have a huge performance improvement. We also see a reduce of loss. So this is the power of using accelerator. The Pytorch XLA enable you to use one of the best accelerators in the market, which is TPU. In this example, we gain about 20 times of the performance by training this model on TPU. Pytorch XLA also provide us some utility tools and packages that help us to debug and see the metrics for the compilation and execution. To access the metrics, we need to import the metrics package, and then we print metrics report and run it. Now we can see the metrics report. It's a long report. We can focus on some of the key metrics. The first metrics that we are interested in is the compile time. It takes about 16 seconds to compile the computation graph, and we compiled 3 computation graphs in total. Interesting part is here, the execute time. We execute 101 times in total, and the total time used is less a second. This is a very extreme example where our training is actually quite short and simple, so that the majority time that we spend is on the compilation. But we can imagine that if we have a huge model and we train more than one epochs, then the compilation time will be insignificant. Here is another interesting metrics. This is a counter that we have 3 uncached compile and 98 cached compile. This explains why the first few iterations is significantly slower than the last ones. That is because we spent a lot of time to trace and compile the computation graph. So it's significantly slower than the last steps. To further optimize the performance, we can use Torch XLA compile to explicitly specify the part of the code that we want to build into a computation graph. So here, our current implementation set a computation boundary at this line. For each of the iteration, the Pytorch XLA system will automatically start building and compiling the computation graph on this line. Pytorch XLA provides us a compile function that allows us to explicitly compile a function into a computation graph. We can start our modification here. We have a self.compile step function. Torch XLA.compile. The compile function takes a Pytorch function and returns an XLA computation that can be executed directly on the XLA backend. So here we have self.step function, and we say we want to compile the full graph equals to true, and we give an optional name for the compiled graph. The compiled function has the same signature as its original function, so we can directly replace where the original function is used. So right here. And then we can remove this computation boundary. Now let's recap what we just did. In the initialization function, we explicitly compile a function which contains all of our training steps into a compiled function. Instead of letting the Pytorch XLA system to guess our computation graph and computation boundary, here we explicitly says everything in this function, we want to turn it into a computation graph. And then with this compiled function, we directly call it in our training group with the same data and target. Now let's run our notebook to see how it goes. Let's start running our definition block, then start the training. Here we see the warning, and then we see it will start training. Still, the first few iterations are slow. And after the first few steps, it runs really fast. So here in the last few batches, we get more than 800 samples per second. Remember that without this modification, we get about 760 samples per second. With our explicit computation graph building, we get even better performance. The first few steps are slow because we still need to trace and compile. An important parameter that we have is here, the full graph. This parameter requests that the entire function can be captured into a single compiled graph. Without this parameter set to true, we might get a partial compilation or multiple smaller graphs. The full graph parameter is often used to capture the forward, backward, and optimizer all in once. By doing that, the compiler has better idea about the overall computation graph that we have and can do its best to optimize the performance. Let's run our metrics to see if that is different from our last time. Here, we still have 88 cached compile and 3 uncached compile. Compilation time is almost about the same. So the approaches that we just demonstrate are very similar. They don't have a functional difference because using compile function can give the compiler and optimizer a whole picture about our computation graph. It can do a better job in optimizing our computation graph. So in general, use the compile function as long as you can. In most of the cases, it gives you the best performance and a higher throughput by removing Python per operation overhead. That's it for our today's lecture and demonstration. Let's back to the slides for a brief summary. In this lecture, we use a real example to show you how to run the ordinary Pytorch code on XLA device. The 3 key things that we need to ensure are that we first need to ensure the data is on the XLA device. Then we need to ensure the model is on the XLA device. Lastly, we need to ensure the trigger is set properly. In our demonstration, we demonstrate a huge gain after running the same Pytorch code with same parameters on XLA device. We gain about 20 times performance. And for better performance, we can use torch compile function to capture the forward, backward, and optimizer all at once. That's all the content for today's lecture. Please let me know if you have any question, and I hope this lecture helps you in your study. Thank you very much. See you in the next video.